Hello, this is Sean Leonard, and today I'll be presenting for Colin Parke and Aref Hakami, and the reason we're doing this is because of the virus, so the three of us aren't able to meet up together, so I will be doing the presentation today. And our presentation is our proposal for recycling the water used in the College of Natural Resources for the golf course water feature. Now, the most important part of this is designing our piping system, and the two important areas of our piping system are in the CNR basement, over here on the left side, and in the cooling plant on the right side here. Now, in the CNR basement, it was provided in the write-up that the water will come out of a tank, and this tank will be provided by the College of Natural Resources. And the tank will provide a flow of approximately 46 gallons per minute, and it's about 6 inches off the floor. Now, next, the water flow will go into this centrifugal pump, and I'll talk more about this pump later on one of our other slides. And then next it goes into this check valve, and this check valve is actually really important because if we're pumping all this water up a long distance in a pipe system all the way up the hill, and this pump were to suddenly shut off or fail, then all that water would start rushing back down the hillside and would probably blow through the pump, might blow up the tank, and could even flood the CNR basement. So this check valve is really vital to be at the very bottom of the water system. And then next, we also have a butterfly valve. And this butterfly valve is so that if like a maintenance worker needs to do work on the piping system or something, they can shut off the flow. Now, next it goes through a 6-foot riser, and because this is a 2D diagram, I don't have a way of representing that in 2 dimensions because this is in a 3rd dimension. So these lines are going to represent our riser, and it's a 6-foot riser, and it comes from the 6 inches off the floor up to 6'6", where it's overhead, and then it can travel through the rest of the room. It travels about 100 feet, and that's where it meets the steam tunnels, and I'll talk a little bit more about that in a minute. Now, inside the cooling plant, we have water coming teed off of the main line, and it comes in through the wall, and it goes through a 5-foot riser. And this is important because this 5-foot riser raises it from the direct burial height, which is 4 feet underground, according to the write-up, up to a foot off the ground, where it then goes through our valve and our pump, and this is our globe valve. And this globe valve is important because it allows you to control the flow coming in from the main water line. And the reason we need this is we need to have variable flow, because the cooling plant is not going to be taking the same amount of water all the time, and in the wintertime it might not be taking any water. And so we need a globe valve to allow us to vary the flow coming in from the main water line. Next, it'll go through a centrifugal pump, and I'll talk about this pump as well later. And it'll flow through and go into another set of risers. Now, unfortunately, we don't actually know the dimensions inside of the cooling plant. We're not given the dimensions, but this is a rough layout of how the piping would still go. And then next, it'll go through a 5-foot riser, and this takes it from the 1 foot off the ground up to the 6 feet. Into the filtration system. Now, we don't know any specs on the filtration system other than we know that the entrance and the exit of the filtration system are 6 feet off the ground. So this will give us that remaining 5 feet we need to be at the right height of the filtration system. Next, the water goes through the filtration system, and the return flow comes back out and goes through a check valve. And this check valve is also important. The reason this check valve is important is because it ensures that when water is not flowing through the filtration system, it can't accidentally backfeed from the main water line, and that would be pretty bad, because if it backfed from the main water line, it's going to be going backwards to the filter, and it would most likely cause damage to the filtration system. So this check valve ensures that there's no backflow. Now, the main stretch of the piping system, right here you can see this is the output from the CNR building. So the CNR building exits to the steam tunnels, and this is where it would connect to the main water line. So the main water line comes out and joins the CNR steam tunnel, where it then goes down to 6th Street. This is the main set of steam tunnels on 6th Street, and then it comes up through the main steam tunnel that goes along the center of campus. As it does that, it then comes along next to the commons, loops around through a separate steam tunnel, and this is where it meets up between the Memorial Gym and the Education Building. The steam tunnel that runs along the path there, and it runs up until it hits the Physical Education Building, and this is the end of the steam tunnels where the direct burial begins. This line right here is the beginning of the direct burial. Now, because the steam tunnels are already underground, they're about 4 feet underground, they are already the correct height for the direct burial, so we did not include a riser here. And then where this arrow ends is where it would reconnect to the line that travels across the edge of campus near the Arboretum. So this would be the edge of the Arboretum behind the Physical Education Building, where it then travels along, crosses the road, and then gets to the cooling plant. So this is where the cooling plant would be teed off, and then the come in line and the return line, and then it comes back out, returns to the length of the 580 feet, until it gets to the edge of the golf course, and this is where the water would then be pumped into the pond, or the water feature as they call it, for irrigation. Now, obviously, in a pipe system this large, we're going to have a good number of head losses throughout the system. So in this case, we have our minor losses, and we have approximately 1790-degree bends, and this is also including our risers that we have to use at a few points. We have 645-degree bends. This is for the 2 points along the length, where you can see that there is the slight S-curves, and then there's also 2 to account for the change in elevation. Now we also have two T's. This is coming off the main water line going into the chilled water plant. We have one butterfly valve, and then we have one entrance. This is the tank inside the CNR facility. Obviously, there's no tank in the chilled water plant, so we don't have to worry about that. And then there's also the exit, and there's also a globe valve, and this is to use to control the water flow coming into the chilled water plant. And our largest head loss by far is just going to be our 90-degree bends. That's not really surprising. And then we also have a pretty good loss coming from our T as well. And we have a little bit coming from our 45s. And these are in feet. This is 16 feet and 4 feet, or approximately 5 feet, 8 feet, etc. Now, I said I would talk about the pumps we chose. Now, our main pump that we chose, and this is the one doing the main line all the way from CNR basement up the hill, is a Bell & Gossett E1531 1.25 AD, and this is the 5 horsepower model. The 5 horsepower model we determined was the one we would need to provide the suitable head. And the cold water plant doesn't require nearly as much head, and so for that reason, we chose the Bell & Gossett E80 1.5.9.5B 3/4 horsepower pump. Now, unfortunately, because there's so much head required in our system, it's around 130 feet for the main line, we had to choose a pump that's not really operating at the most optimal efficiency. Unfortunately, it's only operating about at 50% efficiency. I'll talk a little bit more about that when I get to the system curve. However, since there's less head required, we were able to operate at a higher efficiency on our cold water pump. Now, for our piping system, we chose 4-inch nominal standard piping, and the reason we did this was because inside of our piping system, inside the steam tunnels, there's a limited amount of space, and it's stated in the write-up that in order for us to operate in the steam tunnels, we have to have 2 inches of insulation around our pipe. And for that reason, 2 inches of insulation on a 4 nominal pipe, it brings it out to approximately 8 inches in diameter, and that's about the limit to the space that we can fit inside of the steam tunnel. And so we decided that this was the largest pipe size that we could choose that would meet our water flow, but would also fit inside of the steam tunnel with that insulation requirement. Now, because of the pressure, we chose Schedule 40, and flanged, as it's stated in the write-up, it needs to be flanged if it's over 2.5 nominal, I believe. And also our fittings, of course, they're just going to match our pipe system, so they're going to be 4 standard, Schedule 40, and flanged as well. Now, our system curve, this is what I was talking about with the main pump not operating at super optimal efficiency. Because we're operating in the early part of the curve, it's actually almost just barely curved here at the very end. But this pump is a good example for the cost of what will provide the flow that we need. Now, our cold water pump down here obviously is a much lower head, and for that reason, it is operating at a more optimal point in its curve. Now, fortunately, we figured out that this will provide all of the water that we need. We just chose this pump because we believe for the cost to pumping ability, we thought this was the best deal. Now, for our economic analysis, the cost of electricity is not easy to determine for the university. However, according to Avista, this is the average price of electricity for a facility as large as the U of I, and the U of I uses Avista as their utility. So we think this is a good approximation of how much electricity costs. Now, water, unfortunately, is not generally sold by volume. It's not sold in gallons. It's generally sold as a flow rate, and for that reason, it's kind of hard to determine the cost that the university has in water. So for that reason, we use the $1.5 per 1,000 gallons. This is the national average cost of water. The city of Moscow does not publish how much they charge per gallon, and for that reason, it's sort of difficult to determine what the university pays. But we figured this is a good approximation. Now, the pumps and the piping are obviously going to cost quite a bit of money. The piping especially is around $100,000. It's $93,000, and pump 1 is going to be about $3,500, and pump 2 is around $1,200. Now, for that, in order to calculate our current cost, we took the 46 gallons per minute, and we're assuming it operates all the time, and it generally does, leaving the CNR facility, and we multiply that by our cost of water, and that comes out to $36,000 per year, $36,300, and that's quite a bit of money. That's actually a lot of money in water. And so, using our cost analysis, we discovered that our annual cost, including our piping system and our pumping, including the electricity cost for pumping, was around $13,500, and so that gives us a cost saving of around $22,800, and that is a very sizable cost difference. And so for that reason, we do believe that beyond just being more sustainable, this actually is an economically feasible project for the university to undertake. Now, to go a little bit more in depth into our economic analysis, I'll explain how we arrived at those numbers. So our P, which is our present cost, is our cost of our piping system as well as the cost of our 2 pumps in order to install them. And that comes out to around $97,000, close to $98,000. And we're operating over a course of 25 years and at an interest rate of 2.5%. Now, our annual cost, this is the cost of our electricity, which is to run the 2 pumps, as well as, in order to make this estimate more conservative, we also want to include maintenance. So our maintenance cost is 2.5% every year of the total annual cost, and that's kind of high compared to examples we found in the book, but we wanted this to be a pretty conservative estimate, and so that total, along with the cost of electricity, comes out to $8,100 a year. Now, over time, that comes out to $13,500 when you convert the P to an annual cost, and we still believe this is a good cost savings. Now, the governing equations that we use, the important ones used throughout the project, are specifically pump head, of course, because we're dealing with pumps, and so that's going to be Z2 minus Z1, this is our elevation change, plus our friction factor, times our length over our diameter, times our minor losses. K is our minor losses, and this is multiplied by our V dot in diameter, which gives us our velocity, and this is an important factor in determining our pump head. Now, we also used, of course, our Reynolds number. Our Reynolds number comes out to rho V, which is velocity, d, which is diameter, over mu, which is our viscosity, and our friction factor. This is the Swamy-Jain equation, which is 0.25 log of the relative roughness divided by the diameter divided by 3.7 plus 5.74 over the Reynolds number to the 0.9 power, and that's all squared. And we also use the present to annual cost equation, that's P to A as usually referred to, and this is to convert our present cost to an annual cost over the course of our N. In this case, I said before, our N is our 25-year span, and our interest is 2.5%. And so we actually very much believe that this piping system is feasible and will provide the university not only with the cost savings, but also with a great deal of water savings. And that's important, as the future water is going to get more expensive, especially the Moscow water table is shrinking. And so providing the university with a good way to save water is an excellent use of our resources. Thank you very much.